and sharing my screen. Okay. You guys all seeing the shared PowerPoint slide?
Yeah.
Okay, just want to make sure. Okay. So at request from some of the feedback of someone, some students wanting more goals for each of the lectures or the notes and the like, what we're trying to go over today is autocorrelation and cross-correlation in more detail. We went over it very briefly at the end of last lecture, and I know you guys saw this in Lab 4, and I'm also very aware that you guys completed Lab 4 without having this lecture take place. So I will be aware of that with the grading. But we're going to go over, let's get a more mathematical definition and description of correlation. And an important thing, we'll also go over this visually for different types of signals. If you have a single signal for autocorrelation or cross-correlation, so two signals, can you sketch out and know the expected shape of the correlation plot and also know some quantitative values with that? And I put little asterisks because that will be important for quiz 4. So just pointing that out. Also, correlation has some mathematical similarities to convolution, so we'll cover that, but know that there are applications to using these methods with instrumentation or signal processing that they're different, and we're going to go over those two differences. We'll also talk about correlation both in the time domain but also the frequency domain, which is the spectral power density. So understand that, that's the autocorrelation theorem. And then briefly we'll go into a little bit of detail about different types of noise. So that was also in Lab 4 in Part 5, which some of you guys got through. Some of you also got some data from me. But you guys already got introduced to that, but I'll go in more detail of different types of noise with electronics. That we'll go over in more detail in tomorrow's lecture as well, where the entire focus is on noise. So getting into things with correlation, we talked about this in the last lecture that I guess a verbal definition would be the measure of similarity between two signals, if it's cross-correlation, or a signal with itself, if it's autocorrelation over time. And so yeah, this is in the time domain when you're working with correlation. So if we want to write this out mathematically, what we have is the autocorrelation correlation coefficient here. That's what we're calling g of tau. It's going to be equal to the integral over all time space here of our first signal f of t multiplied times the second signal h of t, and we're shifting that in time, and the amount we're shifting it is this value tau, which is a lag time. And then we're integrating over all time space here, so we have the dt. So with the notation that I have here, you can see that I put xc, and what I mean by xc is that we're doing cross correlation, that f of t and h of t are two different signals. And then this g of tau is what we call the correlation coefficient. And this tau value can be over the entire time space that your signal exists. And that's how much you're shifting. This tau value is how much you're shifting your second signal by here. So that's for cross correlation, but there's also autocorrelation as well. And that's if f of t is equal to h of t. So you have the same signal. And this is then autocorrelation. So if we write this equation out, you can see I notate this with AC here. And we just have the same signal within our integral here. We're again multiplying our first signal times itself, but it's shifted over a certain amount of time, tau here. So we multiply those together, then we integrate, and we get a single value for each tau value here. So you're looking at how self-similar the signal is with itself versus time. So that's the difference between cross-correlation and autocorrelation. And this notation, G sub tau, that I'm using is a convention for using correlation in fluorescence microscopy. That's what I'm used to. That's some of the work I do in my lab. So that's why I use the value G here to indicate the correlation coefficient. So I can also, this is verbal and the math equations here, but we can look at what this means with a graphical representation. And I'm doing this with a top hat function. So here, our x-axis is going to be time. Our y-axis is our signal magnitude. And our starting signal, if we're going to be doing an autocorrelation of a top hat function, that's this purple line here, our f of t. When we're doing autocorrelation, we're going to be shifting that signal with respect to itself by this tau value here. So you can see for a given tau, I'm shifting that signal. That's the red line here. That's f of t plus tau. So this is for a single value of tau. And what we do after we shift this signal with respect to itself, we then will multiply those signals together. So that's what this increase here is. It's a higher magnitude since we're multiplying these two functions together. And so that's the inside of our integral, and then we're going to integrate. So take the area under this curve. So that's what the shaded lines are here. So after we multiply and integrate, then the final step is then to plot this on a different axes here. So this is going to be axes where the x-axis is tau. Our y-axis is our correlation coefficient here. And you can see for the single shift that we did, a single value of tau, we get a single data point here based on multiplying and integrating. So we do this over all of the time space to get a plot of g of tau. So here on our autocorrelation plot at this end, this is where anything less than this value here is when our functions aren't overlapping one another. They then start to overlap, and at a map, and as they overlap more and more, we're seeing this linear increase. And at a value of tau equals 0, that's where our f of t and our f of t plus tau, that would be the same function. So we have a maximum at a time lag of 0. And then after we pass that, they overlap less and less, and we see a linear decrease with the same slope on the other side, since this top hat function here is symmetric around 0. Here. So this is a visual representation of how we're getting the autocorrelation, but we can also think of how would this autocorrelation plot here change as the top hat function pulse width varies. So if we have a wider top hat function, let's say this black line here is in the middle, the red is if it's wider, and the purple is if it's narrower. So these are different f of t's with different pulse widths here. So if we took the autocorrelation of these different top hat functions, if we plot the correlation coefficient versus tau, if we take the autocorrelation, we would see that the slope or over the space of tau here, we would see a positive value over more of tau for the wider that the pulse width is. And this means that the wider pulse, our red line here, is more self-similar over time compared to the narrower pulses. So this is telling you that the autocorrelation gives you information about your pulse width based on the value that it has a positive range. Also, this linear behavior here is telling us that it's a top hat function as well. So I know this is a lot of plots and drawing here. Are there any questions? Does anyone need to see this longer?
I have a question, which is, wouldn't the correlation, the graph on the bottom right, what is the value of g of tau at its maximum? Is that just 1? I mean, what is that value?
Yeah, so that would have to be with like how
is it normalized or?
Yeah, so that would depend. Remember that this is an integral of f of t. If this is at tau equals 0, you just be multiplying those two together. So I guess in these plots here, these are normalized in this plot. by the total area. Well, but it is true that if we're taking the integral of the entire overlap, this red line should actually have, sorry, a higher value than the shorter pulses, if in this plot they're all at the same value. So this is similar to in lab 4, you guys were doing the autocorrelation. There were lots of questions about, and the cross correlation, there were lots of questions about the shape, but not necessarily the magnitude. But because this is an integral, it will scale with the area under the curve. So yeah, this red function here has a greater area under the curve compared to the purple. So this one is normalized. So that's a good point. Any other questions right now? Okay. So we can, yeah. And this point here is just at a longer pulse. It's more self-similar over time. It's slower to the decay in the autocorrelation. So the point I made here with all of these plots, we all see a maximum value at tau equals 0. And this is something that's always true with autocorrelation, no matter what your signal is. With autocorrelation, even if you have noise, a noisy signal, if you take the autocorrelation of this black line here is a noisy signal. If you're doing autocorrelation of that noise, it completely overlaps when tau is equal to 0. There's no shift, so you'll have a maximum value there. But that's not always the case with cross correlation. Realize the difference, that autocorrelation is true, cross correlation, it's not. And for an example of this, we can take a sine wave and a cosine wave. And Flynn, we talked about this, and Rachel, we talked about this a little bit in office hours, and I'll show you that with our f of t here being a sine wave in black, and then our h of t, our second function is this red line, is cosine. If these are our two functions in the time domain, if we then multiply these two together, we'll get something that is symmetric around the x-axis. So then if we integrate, so if we sum all this together, we'll get a value of 0. And this is when there's no time lag. So the functions here are being multiplied and integrated at tau equals 0. So this guy is tau equals 0. So if we plot our autocorrelation of this, we see that tau is 0. For our cross correlation of a sine and a cosine together, but we actually see a maximum value based on the period of the sine and the cosine. So with these two functions where their period is the same, we see that it's 0 at tau equals 0, but we have maximum values at multiples of pi over 2. And then we have 0 at multiples of pi as well here. So this is an example showing that cross correlation is not a maximum at tau equals 0, and it'll be dependent on the functions that you guys have. So being able to identify if you're doing autocorrelation or cross correlation of sine, cosine, or let's say like those top hat signals, those are some of the predictions for quiz 4 you should be ready for. And when you guys are preparing, I mean, I know you guys still have quiz 3 to go, but these were also in the autocorrelation simulations you guys were doing in MATLAB, so it might be worth revisiting at some point, especially after we talk about it in this lecture, or once you get your solutions back for quiz 4, it might be worth redoing some of those sections to remind yourself of what would you expect to see in your autocorrelation plot based on certain signals that you start with. Okay. And I just want to note with that MATLAB simulation that you guys were working in, you can do correlation by multiple ways in MATLAB. The way that we have it in the code that you guys have been using is more by hand, where you can write out the math yourself, where we took our signal, we shifted it by a certain amount. This I is going to be the tau value, and you're summing it over, shifting that signal over all possible tau values. So this is the relevant lines in the code. If you guys go back to that code and take a look, I think they're around lines like 31 or so before you plot. But this isn't typically how people do correlation in MATLAB. There's actually a built-in function. So if you want to have control of your correlation, you can write this by hand in code, and it's simple for like the simple 1D signals that we're working with. But if you're doing something in multiple dimensions or with much larger signals, you might want to use the built-in function xcore. That's built in. So it'd be useful, I just suggest if you decide to use that to also take a look at how that function works and is built in. I know a lot of you guys are working in Python as well, so you know all the background behind how many of the functions work in different languages. But this is just a help file from the MATLAB. If you hit F1, I'm not going to read it to you, but take a look and you can actually like edit the background function. You can actually see that they do cross correlation in Fourier space. So it's by doing it in Fourier space, it's much faster. So that's a perk of using this built-in function. MATLAB also has an xcore too. So this is doing 2D correlation. So if you have a signal that has both X and Y coordinates, you can have tau values in the X and the Y, so you can have different lags. And this is more typically used for image processing applications. So speeding things up, looking at the different capabilities of MATLAB is helpful for correlation. And you can see that if you guys know that MATLAB, that the MAT stands for matrix, if you look at examples online of how people of describing correlation and how it's done, they usually use a simple example of taking two vectors and performing correlation. So let's say we have this vector up here of some numbers. We shift it by a lag of, I guess, one space here. So you would multiply these numbers together. You get these values. Once you multiply all those, and then you would sum them together to get your autocorrelation value at a time lag of 1. So people work through on YouTube to explain correlation through the entire matrix and the entire correlation coefficient. So you can see that like with matrix operations, MATLAB is like very helpful, and being able to do this in Fourier space, speed it up, is useful. So that's just a side note of doing correlation. Yeah.
I still don't quite understand the difference between auto and cross correlation.
So, okay, for example, here this is autocorrelation with this matrix. This matrix here is, or vector, is the same as the vector here. If we were doing cross correlation, let's say we have that same, sorry that my pen is freaking out. We have that same vector, but this would be our f of t. And then we would have some other vector that's completely different, h of t. So you would just be shifting. The difference between cross correlation and autocorrelation is autocorrelation, you have f of t and f of t. You're comparing the same function with itself or the same signal with itself. Cross correlation means that you have two different signals.
Okay. And with autocorrelation, you're comparing the function with itself, but just over like a time lag?
Yes, yes, with the time lag, yeah.
So wouldn't your answer be a function and not a number? Because when you have an autocorrelation over time.
Yeah, so this example that I showed here with the matrix, this is just the value for a time lag of 1. Okay. So then you would shift this over another one. So it would be 1, 3, -4, going on and on. You would get a single value for a time lag of 2. So yes, the output of correlation is always going to be a new function. It's not going to be a single value, it's a new function.
Okay, thank you.
Okay. Any other questions?
So when you write when you're trying to calculate the correlation using the sum, why do you not need to multiply by I, like by the time difference, right? Because you're rewriting the integral in the sum in terms of the sum. So I thought you need to multiply by the delta t or delta I instead of just multiplying the two functions together.
Yeah, there's nothing that has to do with how long your time lag is. So there doesn't need to be any contribution for what your tau value is. Your tau is just indexing how far you've shifted your signal with respect to the other signal.
Like, for this example with the vector, what if the time lag is longer than the matrix? Than the vector itself?
Yeah, so that's where, so this original vector has 1, 2, let me erase this, there's like too much writing.
1, 2, 3, 4, 5, 6.
Yeah, so this is 6,
Yep.
and then once we do once we multiply them together with a shift of 1, there's 5. If we shift it over 2, then we'll have 4 as a result. So it gets decreasingly smaller. So that is an artifact. You guys should have seen that when you were doing the autocorrelation in the MATLAB code. So when you guys were doing, let's say you did the autocorrelation of a sine wave, you should have seen it start to decay. And this decay is because you had a discrete signal. So as you're increasing your time lag, you're adding less and less numbers together. So that's why you see that decay there. If it was a completely continuous signal, this would just keep oscillating. I guess like if it's autocorrelation, it should start at 1. But that's why you see that decay there, because it's an artifact of that you do not have a continuous signal.
Okay.
Sorry, I also have a question.
Yeah.
And if I'm doing autocorrelation with the sine wave function, but right now I add a time lag like 90 degree. So right now I have a sine wave and a cosine wave. Am I still, right now I'm doing cross correlation, right? It's not autocorrelation anymore. So
yes.
Oh, okay. How do you explain this time lag? You said autocorrelation is just like two same function that we can add like our arbitrary time lag into the function, but now by adding a certain time lag, I have like two functions. How do we understand this?
Yeah, so let me go back. Sorry, I guess just slide 2, slide 3. Okay, so just going back to this slide, if this is cross correlation, your f of t, so this would be your sine wave, and then you're saying that your second signal is a cosine wave. Your cosine wave would be the h of t. And then you would just shift one of those signals with respect to one another. So here, if f of t is your sine and h of t is your cosine, you're shifting just the cosine. So the tau comes into play with your h of t. In autocorrelation, you would have a sine and a sine wave. They're the exact same signal, so you would just be shifting that sine wave with itself. So you can think of autocorrelation, the statement here. You can view it also, it's the same, the correlation is the same, just that your two functions are identical.
Okay, so if I shift one of the sine wave by 90 degree, the max value of the correlation coefficient won't be occurring at the tau equals to the 0 point, right?
Correct.
Not in. Oh, okay. Okay. Got it.
Let's see. Okay. Any other questions? Okay, we can move on then. So yeah, I also want to clarify, sorry I didn't animate this correctly, correlation versus convolution, because if you guys remember back to when we were on campus and everything, what our expression was for convolution, it looks quite similar to correlation. So right here, I have our expression for correlation. If we have our expression for convolution, what we have is we have our convolution function here. It's an integral over all time, where this modified time t prime of one function multiplied by another function that's been shifted by this arbitrary value t prime here. So it does have very similar mathematical expressions between these two methods. So there are some differences. One being that with convolution, if you remember, we're using this t prime value, and this has a subtraction value here compared to the plus in correlation. So that means that the second function is being inverted here. So Wikipedia has a great graphic of this, and I encourage you guys to go and take a look at the page for convolution in more detail. To look at this figure, I think it would be helpful. So they have an example where you have two functions. We have f here and g, f being a square wave, g being like a sawtooth type pattern. And if you take the convolution of these two, you can see in the bottom here, they show at different values of t prime, or I guess t here, sorry. They show the overlap between these two functions. So if you remember, if you take a convolution in either order, you'll get the same result out. So this is f convolved with g, or g convolved with f, you get the same resulting c of t out. But correlation has a difference. If you take correlation of f correlated with g, you see a very similar shape to the convolution, but correlation does depend on which function is being shifted with respect to the other one. So if you take g correlated with f, you can see the differences in the shapes being overlapped here, and it will be flipped. So you can get convolution to reproduce correlation if you pre-flip your data and you know that beforehand, but there are differences here. That correlation depends on the order, convolution doesn't. Convolution takes a mirror image of one of the signals that you can see here with the G. You can see that it's being flipped over here. So those are the differences with correlation and convolution. The similarities that have been up here the whole time is, I mean, both of them are taking two signals, with correlation the f of t and h of t, or with convolution f1 and f2. You're taking those two signals and you're producing a third signal out. So the g of tau or c of t. They both have multiplication and integration, but that's really, it's a coincidence that they have those similarities. The application of these are very different, and you should be aware of when to use correlation and when to use convolution. And I think the best way of remembering this is remembering, like, okay, which lab did you apply these to? And when you first were using correlation convolution, we're using it related to understanding an instrument and its response, or we're using it to understand noise. So convolution, which you guys use in lab 3, is all for determining the measurement effect of different signals on one another. So you guys use this in lab 3, where you put some input delta function and wanted to understand how that affected the output for the instrument response function of your filter. How does your filter, the response of your filter, change the output of your signal? So if you're ever trying to understand the relation between two signals, how they affect one another in a measurement, that's when you want to be thinking about convolution. With correlation, what you're using correlation for is looking at similarity or time dependence between two signals or a signal with itself. So a lot of this has to do with like time dependence. And then also correlation is often used in detecting a waveform from noise. So in lab 4, you guys were doing correlation of sine waves with different frequency noise, white noise. And the reason that correlation is used with noise is because noise has a very low correlation with itself. So using correlation to detect a waveform from noise is called match filtering. And that's because for the randomness of white noise, if you're shifting that signal with itself, if it has a very broadband frequency response, you'll have a very fast decay. The broader band of the noise, the narrower the autocorrelation will be. So we can see this. I drew like a noisy signal here, a random noisy signal, and I shifted it over by like 5 units. tau equals 5. That's what's in red here. And you can see where I drew these lines that there's like very low correlation just with this very fast, some white noise that's taking place here. So if you took the autocorrelation and looked at this overlap of this random noise, what you should see is that the autocorrelation here, if we change our x-axis here to tau and the g of tau for the autocorrelation, it drops off very quickly. And if you have access to this optics book, they have a great example. I sketched this right out of there of showing how match filtering works, that you have this very fast decay. So if you have a fast decay of your noise, but then there's also an underlying signal underneath that noise, you should be able to see the shape of the autocorrelation from your signal that would be periodic, which would be extend to much greater tau values compared to the noise. So if you're dealing with noise, stick to correlation. If you're worried about instrument response functions, that's where convolution comes into play. Okay, so also related to noise and characterizing noise, autocorrelation is used with the autocorrelation theorem, which is also referred to as the Wiener-Khinchinyi theorem. You might hear it referred to as that. But it's a way to relate the autocorrelation of a signal to the power density of the signal. So if you remember, this is our spectral power density over here. It's the square of the frequency, the function in frequency. Let's see. Anyone else having issues with noise? Where's my signal connection? Okay.
Oh man.
Is it background noise or just with my voice?
I think something happening with the mic, or it could be some sort of lag happening.
Okay.
I think it's with the connection though.
Yeah, let me check my connection. Give me 1 second. Does the sound any better at all? Or still lagging?
It seems fine for now, I think.
Okay, so I just went and did a internet speed test and it seems like it's okay right now. So hopefully it went down. Maybe it went back up. If you guys have issues again, please, yeah, do what Sebastian did, add some comments in the chat. So sorry about that. Did you guys hear the start of this slide at all? Or should I go back?
Maybe go back a little bit.
Okay. Okay. So here, I mean, the conclusion here was if you're working with noise, use correlation. Or if you're trying to look at a time dependence between some signals, use correlation. If you're trying to understand how your instrument's responding with a given signal, how inputs and outputs are related, then that's when you want to use convolution here. So also related to using correlation to understand noise, we can, that's what's the point of this autocorrelation theorem is. So we've used power density, spectral power density in the past before, where it was more convenient to explain filters. But this theorem states that if you take the Fourier transform of an autocorrelation function, it's going to give you the spectral power density of your signal. So tomorrow we're going to go over using spectral power density to describe noise. But this theorem is a nice trick to be able to get this without having to work in your signal in the frequency space. So the spectral power density is the square of your frequency function. It's going to be related to the power of your signal for each band of frequencies. And it's also a measure of the energy as well. So hence the name spectral power density. So what this autocorrelation theorem allows us to do is that if you have a certain signal, let's go back to that square wave where our function here in time is a top hat function. You can take that signal and you can do the Fourier transform. And with a top hat function, you guys should remember, anyone remember what we would expect with the Fourier transform?
The sinc.
Yes, so if we took the Fourier transform, we would get a sinc function out in the frequency domain. So this is in the frequency domain versus the time domain. But we can also take this signal and we can do the autocorrelation with it, which will give us this triangle shape that we showed before of our autocorrelation. And what the autocorrelation theorem is saying that is if you take the Fourier transform of the autocorrelation function, you can get your power spectrum out, which will be the square. Is this the same as if we took the square, if we raise the frequency function to the second power? So for certain signals where it might not be easy, especially when you guys were working in the frequency domain with imaginary components and the like, sometimes it's easier to take the autocorrelation of your signal and then take the Fourier transform of that autocorrelation to get the spectral power density out, avoiding just working in the frequency domain with the frequency response function here, or the frequency function here.
Professor,
Mm-hmm.
do we have any way to motivate the autocorrelation theorem, or should we just like accept it? I mean, like, is there any sort of like underlying proof for why it works? Or
Yeah, I'm sure, of course, there's a proof behind it. I think that's beyond the scope of what we'll be using it for. We're not going to go into tons of the math, but just be aware that, yeah, autocorrelation can be related to the power spectrum or the spectral power density with this. So, but I can dig around and try to see if there's a proof maybe in the student's guide or the digital signal processing guide. I can look for that and share it with you. Okay. So we'll be using this spectral power density tomorrow a lot to describe our noise response. Also related to this theorem, another one to be aware of, and I know there's a derivation of this one in the student's guide, is Parseval's theorem, or it's also called Rayleigh's theorem after Lord Rayleigh. And this is a relation of the spectral power density, that it's going to be the same as if you are working in the frequency domain or if you're working in the time domain. So this is the general form written at the top. If you have two functions, f of 1 in the time domain times the complex conjugate of f of 2 in the time domain and integrate over all time, that's going to be equivalent to integrating the same functions that are Fourier transformed in the frequency domain. So phi 1 in frequency times 5, the complex conjugate of 5, 2 in the frequency domain and integrating over all frequencies. So, I mean, to me, this makes a lot of sense when you're taking a signal in the time domain and you're Fourier transforming it into the frequency domain, you're not changing that signal. You're just looking at a different representation of it. So it makes sense that the total energy in your signal, total power of that signal is going to remain the same as if you're looking at it in time or if you're looking at it in frequency. So this is another theorem to be aware of as well. And I think this was brought up in some earlier labs just in passing, maybe at the end of lab 4 a little bit. So that's another one to be aware of. So with that, I just want to give a couple examples of how correlation is used, cross-correlation or autocorrelation, I guess in the real world or in the research world. And in the digital signal processing guide, they give this nice example of using correlation for radar. If you have some satellite that's sending out some signal to try to detect something that's far away, you send a burst out. Let's say for the military, they're detecting some aircraft. It'll hit that aircraft and then reflect off and then be received at a separate satellite receiver. So if you have these signals, if you know when you sent this signal out and then you detect this signal, you can do cross correlation between the two, and then knowing like the speed of light, you can then determine how far away that object is. And I think this is a very nice, simple example that's very important, which shows that just cross-correlating those signals in time, that's going to give you like the time dependence between the two, which you can then relate to distance. So that's, I guess, a very macro scale application, but a more nanoscale application that I've actually used in my research, I'm using in my lab is something called fluorescence correlation spectroscopy. So the fluorescence is that you have this focused laser beam right here, and this is, you know, the size of this focus spot. And then you can have fluorescently labeled molecules. Here I've shown some like little proteins that are diffusing around, but people will also use this on cell membranes. And when when there's proteins and they're not in this focal volume or this laser spot, you don't see anything, but when they enter here, they're going to emit a bunch of light, and then they'll pass through your sample and you'll collect that light on a detector. So just like in our class, we're getting 1D signals, here you would get a 1D signal where each of these bursts, that's telling us that there's like a protein there. And then you can take the autocorrelation of this signal and you'll have a decay. So this is our G of tau here. And this is our tau on X. And based on how large your object is or how confined or crowded it is, you'll see different decays in the autocorrelation curve. So here, this would be something that's diffusing really fast, like these 2 nanometer molecules. You see these little bursts. But you can imagine if something's bigger, it's going to diffuse slower through this focal volume. So you'll see more intensity versus time. So then when you shift it over, just like we were doing with the top hat function, or the top hat function before, you'll see that decay slower. So you can relate the decay of this curve to like the size of something, its diffusion coefficient, and quantify things in a lot of biophysics applications that way. So that's one application where you're getting dynamic information, diffusion information, but also in biophysics, people will use this in image analysis as well. So this is an example of electron microscopy images. So I'm just going to say EM, that's electron microscopy images of this barrel-shaped protein. So you can see that there's top-down views of the barrel and then side views, and they were able to take some example images and then just do 2D correlation where they would take this image, scan it across the larger field of view, and then identify where those proteins are at. So for a small field of view here, it's not that difficult to do. I'm going to guess that the barrel size here is probably like 5 nanometers or so. So for a small field of view here, it'd be easy to count by hand, but imagine you have tons of images. You're trying to count tens of thousands of these. It's much easier to have the computer do it with correlation compared to doing it by hand. So that's most of what I wanted to cover with correlation, but I also wanted to introduce a few things about noise and different sources of noise, which you guys covered in Lab 4 at the end there. So you guys worked with like the resistors and looking at thermal noise sources. And tomorrow we'll go over into more, I guess, the power spectrum of each of these noise sources and what types of noise they are. But the first type of noise is thermal noise. You'll also hear it referred to as Nyquist or Johnson noise. And this has to do with electrons being produced in resistive components in your circuit due to thermal agitation. So you guys saw that the equation, I guess this doesn't average out to 0, so ensemble averaging can't help you here. And the quantitative relation between the amount of noise that you see in your voltage, as VRMS, is related to the square root of 4 times the Boltzmann constant times the temperature, the resistivity of the component, and your bandwidth. So I've written all those out here, T being the temperature. Typically, I think you guys use this in Kelvin, but check your units. R is the resistance of the noise source, hence why you guys were changing, like using like a kilo ohm, mega ohm, giga ohm resistors, and B is the bandwidth of frequencies that you're looking at. So the fact that the bandwidth is in here, where it's the square root of B, it doesn't matter which range of bandwidth that you're looking at. So this is indicating to you when you look at this equation that this is a white noise source, that it's uniform as a function of frequency. Similarly, there's another white noise source when you're doing electronic measurements that's called shot noise. And this is where your modern physics comes into play and you see some quantum effects at the macro scale a little bit. So when you're measuring a current, what you're having is you're detecting individual electrons that are passing through your circuit. So these electrons, they're quantum objects. There's going to be statistical fluctuations that typically follow a Poisson process because they're quantized events. So that's usually like an exponential or so. But this shows up then as the shot noise effect is the name that's applied to it. So the statistical fluctuations here, we typically characterize it based on the current instead of the voltage. So here, the root mean square of the current that you're seeing is going to be the square root of 2 times the fundamental charge of an electron times your average signal over time, is I dc, and then the bandwidth again. So your electron charge is 1.6 times 10 to the negative 19th coulombs. And again, we see with the bandwidth that we have this square root of B. So once again, this is going to be a white noise source since it's uniform across whatever frequency range you're looking at. So these are going to be the 2 white noise sources when you're actually doing an experimental measurement, if you're not just using your R to feed in a white noise source, because that's not typical where you just like feed a noise source in, but this is where you'll actually see white noise. There's also 2 non-white noise sources. One is called flicker noise. This can have to do with the type of resistors that you're using. It shows up in a lot of types of measurements, and there's not really a well understood cause to try to improve it. Different electronics have different sources of this, but this one is called 1/F noise. So this is not a white noise dependent. It's not, it has a frequency dependence, so it is not white noise. And it'll show up in a plot like this. And we'll go over this in more detail tomorrow of how you would plot noise, but I brought this plot up here because you'll only see white noise around frequencies less than 100 hertz. So if you're doing a measurement that's at very high frequencies, you don't have to be concerned about flicker noise. The problem is when you're less than 100 hertz. You'll start to see this 1/F, or the linear dependence if you're plotting this on a log scale. So you can see the y-axis here is log, the x-axis here is log. That's when you see this linear decay. And then finally, the last source of noise is environmental noise. That all of the electronics in your setups, they can act as a conductor for, or an antenna, so they can pick up a lot of different frequencies that are around us. So the ones that you should be aware of or most frequently observed are going to be the 60 hertz signal. That's a big one of our power lines around us and the delivery of electricity, but also depending. So the question from Neil is, the white noise is what, 100? Okay, so to clarify this, less than 100 hertz. Okay. Yeah, I'll clarify here. So, okay. So the point here is, because my handwriting, this pen is too noisy, I guess. Flicker noise is not white noise. So, because it is not like uniform over all frequencies, because it has this 1/f dependence, and it's 1/f when it's less than 100 hertz. That's what we're seeing over here. It's not a white noise source. And tomorrow we'll talk about what color noise it is. So to reiterate, flicker noise is important below 100 hertz. So I hope that answers your question. The last things with the environmental noise are radio signals as well. So just be aware that in the kilohertz area is AM radio, in the megahertz area is FM radio. So when you're looking at these different ranges of frequencies, these are some of the environmental sources you'll see. And again, these aren't white noise signals. So if we're saying like white noise looks like this, you'll see like spikes for the environmental noise for like 60 hertz or at these different radio signal frequencies. So again, tomorrow we'll talk about plotting these and visualizing them there. So I think that's most of what I wanted to cover. Okay, yeah, you have a question, Noah?
So like if you know that you have environmental noise, couldn't you just add some kind of filter onto all of your circuits that filters out all the AM and FM radio frequencies, unless you think that those frequencies are also going to be part of the signals that you're collecting? I mean, couldn't you just filter those out?
Yeah, exactly. And tomorrow, that's what we're going to be talking about. That's a great lead in, that we'll be talking about how can you reduce effects of noise. And especially when you're aware of, okay, we're going to see a strong 60 hertz signal, or we're over by the signal for 91.1 WRUW is strong around here. Like, you can block out certain ones that might show up. So we'll talk about that more in detail tomorrow. Okay, cool. So any other questions from people? Okay. Let me stop recording. Stop sharing.